And we wrap up the chemistry chapter, Chemistry of Life, with part 4, talking about acids and bases and how those affect pH. Also looking at inorganic versus organic macromolecules. Acids, bases, and salts. Electrolytes are substances that release ions in water. That's the dissociation by water into components of cations and anions. Electrolytes can conduct electrical currents while in solution, and that's the definition of electrolytes. And we've already talked about sodium chloride before. Sodium has this positive sign because it's a cation, because it gave up a electron, its valence electron, to chlorine, and then it became chloride, an anion, and these two are now stable, and an ionic bond was formed between that sodium and chloride, and these disassociated in water or came apart in water, and we see that these are the products of sodium chloride in water, sodium and chloride electrolytes. Acids dissociate into one or more hydrogens and one or more anions. Electrolytes, these are electrolytes that release hydrogen and water. Bases are binds with hydrogen when dissociated in water. Some dissociate into cations. And here we had sodium hydroxide. That is a hydroxide ion, OH. And sodium hydroxide dissociate in water, and there you have OH. Okay, hydroxyl ions. Salts. Electrolytes formed by the reaction between an acid and a base. So we have, this is hydrochloric acid and sodium hydroxide. An acid, sodium hydroxide, this is a base, reacting together, and it has a byproduct of water and salt, sodium chloride. And so the base, the acid plus the base yields water and salts. Salts, compounds that dissociate in water into cations and anions other than hydrogens and hydroxides are called electrolytes. This process is called ionization, and if you pick up a box of salt from the shelf at the grocery store, it may say ionized salt or ionized salt with iodine added. It is a important component to many enzymes. It has electrical energy generated by the movements of ions across the membranes, and we'll talk about that with the nervous system and muscle contraction. Transmits messages through the body, information on nerve impulses. So again, the definition of electrolytes is dissociated in water into components of cations and anions. Electrolytes can conduct an electrical current while in solution. Let's look at a pH scale. It indicates the concentration of hydrogen ions in solution. Hydrogen ions in solution. Acids are electrolytes that release hydrogen in the water. Neutral, pH 7, indicates equal concentration of hydrogen and hydroxyl ions. Acidic, the pH is less than 7, indicates a greater concentration of hydrogen. So right here is neutral, and as you go to lower numbers, it increases in acidity from 6 to 5, 4, 3, 2, 1, 0. basic or alkaline has a pH greater than 7 indicates there's a higher concentration of hydroxyl ions as compared to hydrogen ions. And the concentration of hydrogen ions in solution is expressed using this pH scale. It's based on a logarithmic number by tens. So a hydrogen ion concentration difference between solutions of pH 2 and pH 3 is tenfold, and between pH 2 and pH 4 is 100 times fold, and 2 to 5 1,000 times fold. So it is based on the rules of tens logarithmically. And what does pH stand for? Potential hydrogen. So this is a scale, a logarithmic scale that shows us potential hydrogens. It's always written with a lowercase p and a capital H. So it's misspelled if you capitalize the p. Potential hydrogens, hydrogen, the H is capitalized because it is the symbol for hydrogen. And just to review again, neutral has equal numbers of hydroxyl to hydrogen ions, and so its pH is 7. And as your pH numbers are reduced from 7 to 6, 10 times, from 7 to 5, 100 times, from 7 to 4, 1,000 times more acidic. So the lower the number by times 10, 10 times more for each of those pH numbers below -7. And alkaline or basic, and both of these terms are correct. The pH is greater than 7, so pH 8 is 10 times more basic than neutral. And then between pH 8 and 10, it would be 10 times 10, 100 times. So pH 8 compared to pH 10 is 100 times. pH 10 is 100 times more basic or alkaline than pH 7 or pH 8. 7 is neutral, equal in numbers of sodium, equal in numbers of hydrogens and hydroxyl ions. Okay, so metabolism requires relatively constant balance in acids and bases. It depends on where in the body the location of, like in your stomach, is very acidic, but in your gut, after you've digested your foods, they move to the small intestines, but you have enzymes and buffers added to reduce some alkaline buffers and enzymes that help to reduce the acidity, because if we did not reduce the acidity of what comes out of the stomach to the small intestines, then our digestive fluids will digest our small intestines. And your mouth has a different pH than your stomach, and the esophagus different pH than in the large intestines. So a constant balance of pH in those places is very important. Buffers prevent drastic changes in the internal pH. Now, I help to prepare media for microbiology. We add buffers to our media. Now, I do get pre-mixed media, and so the buffers have already been added. But the reason why we add the buffers is because when those microorganisms are metabolizing in that agar or in that broth, tryptic soy broth or tryptic soy agar, they produce acids and bases, and it changes the pH of the media. So if we didn't have buffers in there, they would kill themselves very quickly by producing acids and bases during their metabolic processes. So we add the buffer, and those buffers prevent drastic changes in the pH in that media that they're growing in, so that the students can view those organisms for a longer period of time, more than just a day or so. So we have natural buffers in our bodies that help prevent drastic changes of pH. Acidosis versus alkalosis. Your blood has a pH of about 7.4. Now think about 7.4 on that pH scale. So what would be the pH? Would it be neutral, acidic, or basic? Well, 7.4 is a little higher, a higher number than 7. So your blood is slightly alkaline or basic. Okay, so if your blood pH is less than 7, 7.4 to 7, a little bit, but if it's even lower than pH 7, say 6.8 or so, we call that acidosis. If your blood pH is above 7.6 or 7, it is considered alkalosis, more alkaline or basic. Now, this can happen if there are pH problems in the body, if those buffers, those enzymes that act as buffers are not acting right, if the liver's not functioning right, if the pancreas makes some of these enzymes in the liver, and if it's not functioning correctly, then acidosis or alkalosis can happen, a change of the pH of the blood. And just like all other metabolism that needs a pretty constant pH in the area that it's happening, your blood needs to maintain a pH of 7.4 at all times. So acidosis is when the blood's too acidic, so a pH below 7.4, and then alkalosis is a pH above 7.4. Now here we have some common household items. We have, let's see, the apple juice. And apple juice has a pH of about 3. And grapefruit juice, soda, pH between 2.5 and 3.5. They're pretty acidic. Lemon juice, a 2, and vinegar also. Battery acid and hydrochloric acid. And by the way, this is about where the acidity in your stomach is. Okay, so this is extremely acidic. More neutral here. Seawater has a pH of about 8. There's blood there, 7.4. We talked about that. So if it's higher number than 7.4, alkalosis, and a lower number than 7.4 for blood pH number, it would be acidosis. Baking soda, 9.5. You can neutralize the acidity of something if you had a spill with baking soda. Ammonia is 10.5 to 11.5, and very caustic. So is bleach and oven cleaner and lye and liquid drain cleaner. Extremely caustic and very basic at pH 14. Just some common household items. Milk of magnesia is around 10.5, which is interesting. It's what we drink to, milk of magnesia when you have an acid stomach. So it's more basic to help to counter that acidity in your stomach. And this is from an article that talks about alkalosis and acidosis and the metabolic problems that reduce the level of functions of buffers that act as bases, and they promote the production of acids. Read about this so that you will know more about acidosis and alkalosis. Kidney failure, liver failure, heart failure, cancer, and other disorders can prompt metabolic acidosis, and alkalosis, almost the same thing, but respiratory alkalosis is when you have lung disease, aspirin overdose, shock, and ordinary anxiety can cause respiratory alkalosis, which reduces the normal concentration of hydrogen ions, therefore making the blood pH higher than 7.4. Metabolic alkalosis often results in prolonged severe vomiting, which causes loss of hydrogen and chloride ions, which is hydrogen chloride, that is hydrochloric acid. Medications also can prompt alkalosis. Diuretics, when you lose the potassium ions, as well as overuse of antacids. And the person with persistent heartburn or an ulcers that is using a lot of antacids and prescription medications can have metabolic alkalosis. Organic versus inorganic. Organic molecules contain carbon and hydrogen. Usually is larger than inorganic molecules. It dissolves in water and organic liquids. Carbohydrates, proteins, lipids, and nucleic acids are very important to us, and these are all organic molecules. Inorganic molecules generally do not contain carbon. Usually they're smaller than organic molecules. They usually dissolve in water or react with water to release ions. Water, oxygen, carbon dioxide, and inorganic salts are all inorganic molecules. So water, inorganic or organic, H2O, it doesn't have the carbon, and so it is inorganic. And by the way, water is the universal solvent that things dissolve in, and that's what we're going to look at next. Most abundant compound in living material, it makes up 2/3 the weight of our body. Major component of all body fluids. We talked about those serous fluids between the serous membranes. Mostly water. Medium for most metabolic reactions. Important role in transporting chemicals throughout the body. Can absorb and transport heat. Regulates body temperature. Universal solvent that things are dissolved in and moved in. And it's also very cushioning. It makes up 60 to 80% of the volume of your living cells. 60 to 80% of the volume of your living cells. And because it takes a very high amount of heat energy to change water temperature, it helps to buffer against rapid temperature changes in your body. We know this because we, for the most part, are close to Lake Texoma, and in the early summer, that water is pretty cold or maybe pretty cool, and then in August and September, maybe late September, the temperatures begin to drop and it may be very cool, but yet you get into that water and it feels like that it's like bath water. So it's very warm even though the ambient temperature or the outside temperature is cool. And it takes a long time for that body of water to heat up with the sun and to cool down. And so water in our bodies help to maintain our body temperature and helps to buffer against rapid temperature change. Oxygen is used by organelles. It's used in the body mainly to release energy from glucose during cellular respiration. So it is mainly used to release energy from glucose during cellular respiration. Used by the organelles to release energy for nutrients, and it's necessary for survival. Inorganic substances continued. Carbon dioxide. It is a waste product released during metabolic processes, and it must be removed from our body. The only good thing is it helps to provide some of the buffers that we talked about that keep pH level, and that's about the only good thing about carbon dioxide. The carbon dioxide must be removed from our bodies. Inorganic salts are abundant in body fluids. We talked about the electrolytes. There's sodium, chloride, potassium, calcium, that K is potassium, calcium, etc. play an important role in metabolic processes. It also makes those trace elements that we talked about before. It's important for nerve conduction, muscle contraction, and we will talk more about those a little bit later. Organic substances provide energy for cells. It supplies materials to build cell structures. It's water soluble, dissolves in water, contains carbon, hydrogen, and oxygen. The ratio is close to 2:1 between the hydrogen and the oxygen. There's that glucose molecule that we talked about before, 6 carbons to 12 hydrogens to 6 oxygens. That 2:1 ratio there indicates that it is a carbohydrate. Monosaccharides. Mono means one. Saccharide is a sugar. Fructose and glucose are very important to us, monosaccharides. They're easiest for us to use. In fact, we cannot use disaccharides or polysaccharides. They must be broken down into monosaccharides. So glucose is the most important to our body. Our nervous system likes to get its energy from glucose exclusively. Now, other areas of our body can get energy from other sugars and other amino acids and things, but our nervous system uses glucose exclusively. Fructose is another monosaccharide. These are simple carbohydrates or sugar. They're simple sugars, meaning there's only one sugar, and they're used by our body quickly for quick energy. Fructose would come from like orange juice and honey, and we can use that orange juice and honey very quickly, but here's the thing about that: it's very quick, provides very quick energy, but it's used up quickly also. Disaccharides, 2 sugars, sucrose and lactose. Have you seen that word before? Milk sugar. Okay, sucrose is like table sugar. Lactose is found in milk. And these are disaccharides. So for us to use them, we have to break the sucrose down into monosaccharides so that our body can use them. We can't use sucrose and lactose directly. It has to be broken down into a monomer. A monomer is monomer. A monomer is the simplest. So glucose is a monomer, fructose is a monomer, sucrose is a disaccharide that has to be broken down before we can use it. So it does provide energy, but it takes a little longer because the sucrose has to be broken down, and the same with lactose has to be broken down before we can use it into monosaccharides. Polysaccharides has long chains of bonded together monosaccharides. Poly means many, saccharides, many sugars in a long chain. And I believe in lab I talked about this. And so when we are digesting our food and we glean those monosaccharides from our food, especially glucose, are what happens when we eat carbohydrates and some amino acids in proteins. Our body will release, the pancreas will release insulin, and that insulin helps us to utilize that glucose. And glucose that's not utilized is changed to glycogen, takes those glucose molecules and bundles them up into a polysaccharide and stores it in the muscles and the brain. And so the pancreas, when we need glucose, when our glucose levels drop, like I said, that the nervous system likes glucose exclusively, and we need more glucose because our blood glucose levels have dropped, then glucagon is released by the pancreas that breaks that glycogen that's been stored in the muscles and in the brain down, release the glucose from it and many glucose molecules back into the bloodstream to raise that glucose level. Okay, cellulose is unique. It's a very long strand. It's very complex, cellulose. Now, where you would find cellulose, where do you find cellulose? Yes, it's in your diet. And guess what? Your digestive system cannot break down cellulose into monomers. It can't break it down. It's unable to break it down. So cellulose is found in plant fiber, plants. And so we need cellulose in our diet. Why in the world would we need something in our diet that we can't break down? Have you ever heard of fiber and being regular? Fiber's very important for our gut and the health of our gut. So we take in fiber, that cellulose, that helps keep us regular. Sugars are used to hold adjacent cells together. It is used for energy. It is used on the surface of cells for holding things together, for communication between cells. It plays an important role in cell structure also. Now these are structural formulas. Again, a monosaccharide, here's a monosaccharide. It's has an easily broken bond, so that carbon 6, hydrogen 12, oxygen 6, C6H12O6 is a simple carbohydrate, monosaccharide. And disaccharide requires more energy. Now here's the thing about a disaccharide and even a polysaccharide. It provides more energy, but it takes more energy to break it down into monosaccharides, those monomers. And yeah, it takes a little energy, but you have a longer lasting energy because you have 2 sugars here as compared to 1, and then a polysaccharide. So you have a football player who's going to play in a game on Friday night. So Thursday night, he eats spaghetti and pizza for supper, and that spaghetti and pizza's got a lot of starch in it, and that starch is it's a polysaccharide and has a lot of sugars bonded together. So while those things are being digested, it releases a lot of sugar to be used with metabolism for energy. And if you are not an athlete, then a lot of that sugar is going to become glycogen, and if glycogen's not used, it becomes fat. But for an athlete who needs extended time of energy to participate in their sport, then they need the polysaccharides. Most difficult to break down but provides the most energy. Glycogen is a polysaccharide. Animals store in muscle and liver. Also for future use, and we already talked about cellulose, the fiber that cannot be broken down. You know, even a termite cannot break down cellulose. It has a little organism in its gut that helps to break down the cellulose when it's eating the wood in your house. And starch that we use as an energy source is a bunch of sugars bonded together, and as it's broken down, we can use those monosaccharides from that polysaccharides for an extended period of time. So see those different shapes? Okay, now continuing with organic substances, lipids. Lipids are fats. They're soluble in organic solvents or fats. Fats are triglycerides. Triglycerides consist of 1 glycerol and 3 fatty acids. Here's the glycerol portion and the 3 fatty acids. So a triglyceride, 1 glycerol, 3 fatty acids. 1 glycerol, 3 fatty acids. Gee, I'm repeating myself, so there must be something on the exam about that. Okay, it's used primarily for energy. It contains carbon, hydrogen, and oxygen, but look at this ratio here. Remember that 2 to 1? Well, this isn't 2 to 1. It contains much less oxygen than carbohydrates does, so it doesn't have that 2 to 1 ratio. And again, the building block, 1 glycerol and 3 fatty acids per molecule. You have saturated and unsaturated. Okay, this also includes the phospholipids, cholesterol, fats. It's not soluble in water because water is not organic. So tri means 3 fatty acids, glycerides. Saturated is solid at room temperature. Animal fats such as lard is a saturated fat. The fatty acids are linked to arterial sclerosis, so they're not good for us. Unsaturated is usually liquid at room temperature and is better for us. Unsaturated, the only exception to liquid at room temperature, and you may already know this if you have this in your cabinet, coconut oil is usually a solid at room temperature. And now it is an exception to the rule that it's a solid, and some say it is not good for you, and then some say it is, so the jury is still really out on this. Phospholipids look very similar to that triglyceride. It is similar, but it only has, this is a glycerol portion, and the phosphate portion, 2 fatty acids and one phosphate molecule, okay, is a phospholipid. Building blocks, 1 glycerol, 2 fatty acids, and 1 phosphate. 1 glycerol, 2 fatty acids, 1 phosphate, phospholipid. It's hydrophilic or hydrophobic. Okay, next chapter we'll look at is the cell, and when we're looking at the cell membrane, it is hydrophobic and hydrophilic, meaning water-soluble head means water can penetrate through, but then the tail is insoluble to water, so it is a phospholipid bilayer, so you would have the head sticking out this way and the tail this way, so it really forms a barrier to water and things that are transported in water. So that cell membrane is not soluble or does not allow water to diffuse through it, and we'll talk about that in the next chapter. The tail is hydrophobic. To translate that means it's afraid of water, and hydrophilic is water soluble. It allows water to go through. Okay, so the tail The tail is hydrophobic and the head is hydrophilic. So the phosphate group is water soluble, and that's what makes up the head. And the fatty acids, and we know acids are not soluble to water, it's insoluble to water. So the phosphate is, and the fatty acids are not. And so this would be the phosphate part, and this would be the fatty acid part. Steroids have ring-shaped flat molecules. The steroids are in membranes that help stabilize them. It synthesizes other steroids. Some hormones are steroid-based, like sex hormones. Also, the synthesis, we need to synthesize vitamin D, and that is synthesized by a steroid. Vitamin D is very important to us because we have to have vitamin D in our small intestines, and if we don't have the vitamin D, we are not able to absorb calcium. Even though we take calcium in our diet or in a vitamin, we would not be able to absorb it unless we have vitamin D in our gut. Cholesterol helps to stabilize the liver as well. It helps to stabilize the cell membrane. It's synthesized or made by the liver, as well as obtained in the diet. Cholesterol is a type of steroid. Remember, they have that ring shape. In the AMP2, you'll have to recognize one of these. They have the rings of carbon. Okay. And the amount of cholesterol that you make is hereditary. And so sometimes people who have a very good diet, low in cholesterol, still have to take cholesterol medication because their liver produces more than what it should, and that is a hereditary thing. Proteins or structural materials also acts as an energy source. High protein diet, some people use high protein diets for weight loss, and so that protein becomes the energy source. Many hormones are proteins. The amino acids forming one or more polypeptide chains, and we'll look at that in just a minute. Receptors on the surface of cells and different areas of your body, we talked about receptors before, are made up of hormones. Enzymes act as catalysts. We talked about that before. A catalyst is something that's not used up in the reaction, but it causes the reaction to happen or speeds up the reaction, and maybe that reaction wouldn't happen without that enzyme, and that enzyme is usually a protein. Antibodies for your immunities are built by your immune system, and they are proteins. The building block of proteins are amino acids. Amino acids are held together by peptide bonds. So we have one amino acid here, the general structure of an amino acid, and notice that you have this hydrogen here, and when we were talking about hydrogen bonds, there's a hydrogen here. Hydrogen bonds are easily formed and easily broken, so this is a amino acid linked together by this peptide bond, and in this peptide bond between this carbon and the nitrogen with this hydrogen is easily formed and easily broken. So when we eat our proteins in our meals, it can be broken down into polypeptides. Is a long string of amino acids. A protein is a long string of amino acids. A polypeptide is a long string of amino acids, and then down to a di, which means two amino acids, down to the amino acids. So proteins are made up of many, long string of amino acids. Okay, amino acids, and when we have two amino acids, that's called a dipeptide. Okay. Amino acids, their structures is carbon, hydrogen, oxygen, and nitrogen, and sometimes sulfur. Nitrogen is unique to proteins. Nitrogen is unique to proteins and amino acids. There are about 20 different kinds of amino acids. A protein may have more than 5,000 amino acids in a long string, held together by hydrogen bonds again, easily formed, easily broken. So we've got to break down that protein that you had into polypeptides and dipeptides to the individual amino acids. And what do? We're recycling machines. We make more protein, cell parts, tissues, and hormones and enzymes and receptors and all this. We build from those amino acids that you got from your diet. We build new proteins from what has been obtained from breaking down proteins. Okay, so what happens here? You have a primary structure. Proteins, these are polypeptides. Remember, two amino acids would be a dipeptides, but after two, it becomes a polypeptide. As we build this protein, the peptide bond forms between each amino acids, and then the secondary structure, the polypeptide chain of a protein molecule, is often pleated and twisted into a coil, and the dotted lines represent those hydrogen bonds, easily formed and easily broken. Then tertiary structures, that pleated and coiled polypeptide chain will fold on itself to a unique three-dimensional shape. Quaternary structure, two or more polypeptide chains are connected to form a single protein. The shape of the protein, the unique three-dimensional shape, determines its function. So if this is denatured for some reason, what does denatured mean? And you need to remember that word. Okay, so for breakfast this morning, you cracked an egg into a frying pan and turned on the fire underneath it. When you turned on that heat, it denatured the protein in that egg, that clear white of that egg, in that raw egg. It turns white after you add heat. You are denaturing the protein of that egg. Now, denaturing, does it mean that it's not a useful protein to us anymore? No, we can use that protein. We break down that protein for the amino acids and we use them to make more proteins. It's still useful for us, but some purists would say, you don't need to cook your eggs, you need to eat them raw. It's a different protein, and that is correct. It's a different type of protein. You don't have to eat it raw. The protein, after it's cooked, it does denature into a different protein, but it's still good for you. It's one of the cheapest and readily available best sources of proteins you can have. If you can't afford a whole lot of meat, buy some eggs. Okay, so the yolk is mainly lipids, but the white is called albumin, and it is a protein. And what can denature things in our body? Running too high of a temperature. That can cause denaturing of proteins and damage. Radiation, being electrocuted, various chemicals, and that includes chemotherapy, those chemicals found in chemotherapy. We'll look more at proteins in the next chapter when we talk about what happens in the cell. Remember carbon, hydrogen, oxygen, nitrogen, and phosphate? Well, we need those for nucleic acids. The building blocks are called nucleotides. So what is the monomer of a nucleic acid? nucleotides. The monomer of a nucleic acid is a nucleotide. Okay, general function is genetic code. Nucleotides are the building blocks of the nucleic acids, or nucleic acids are composed of the building blocks called nucleotides. There are 3 parts to that DNA. There is adenine, guanine, cytosine, thymine, and then in RNA it's adenine, guanine, cytosine, and uracil. You have a sugar, a base, and a phosphate. See, this is pentose shape. That's a pentose sugar. A nitrogenous base, nitrogen-based base, and a phosphate, and a phosphate group. So DNA has thymine and RNA has uracil. If you wanted to remember, and we'll talk more about this when we talk about protein synthesis in the next chapter. Okay, nucleic acids. So here are the strand of nucleic acid. The molecules of ribose and deoxyribose differ only in a single oxygen atom. Their structural formulas, the dotted line indicates a hydrogen bond. Remember what we said about hydrogen bonds, so that dotted line, easily formed, easily broken. And DNA is found in the nucleus. It is the blueprint or instructions for double-chain nucleotides, or instructions for building proteins. The order of the amino acids come from the information found in the nucleus in the DNA. So A, G, C, T are the bonded bases. We'll talk more about in the next chapter. It instructs or gives the pattern or the map or the recipe for building proteins, which proteins to build, when to build them, where to build them. RNA is found in the nucleus and in the cytoplasm. It copies the instructions and uses them to build proteins, protein synthesis. Ribose, RNA is ribose, a single chain of nucleotide bases is adenine, guanine, cytosine, and uracil, as I mentioned before. But we will look at this again in the next chapter. Okay, before we leave this chapter, I want to talk about this equation that is on the board. ATP, our universal energy carrier for our body. We can conclude that one more chemical in our cell, and that you've heard of before, is ATP. We'll discuss this more as we go along. It's the universal energy carrier in our body and living things. It's energy taken from breaking down food and cellular respiration. And so look at this equation. Remember that the arrow is pointing toward the product. So what type of reaction is this? Just in review. Decomposition. Why? Because you have a more adenine triphosphate. Adenosine triphosphate down to adenine diphosphate plus a phosphate. This ATP is a larger, more complex molecule that is broken down into 2 simpler. And when that happens, energy is released. So it's decomposition. It's exothermic because energy is released. And it's catabolism. Okay? But I could draw another arrow, and that arrow would be pointing back toward ATP, because in cellular respiration we phosphorylate that ADP into ATP, and where we can use this all over again. And remember, if the arrow is going this way, it's synthesis, and you need energy for this to happen, and then the energy is stored here. Well, guess what? We can make all the ATP in the world, but it doesn't do us any good. Oh, wait a minute, Miss Popwell. We've got to have ATPs. That's our universal energy carrier. That energy is not utilized or released to be utilized until the bond between these is broken and that energy is released. So it requires energy to go this direction. To make the ATP, you have to have energy. So if you're going this way is synthesis, it's anabolism, and it is endothermic. It's added. Endothermic is added energy, and it's just sitting there and waiting until we need it, that energy to be released, and it goes this way: decomposition, exothermic catabolism. And that's all for chapter 2.